Morning. Okay, on the board is today's attendance question. You have a limit at infinity, x approaching infinity. We're trying to find the ratio between 3 minus root of x divided by 2 times root of x plus 5. So when x approaching infinity, you can imagine like x is taking on an increasingly large number. It's possible to try to estimate the limit value by choosing large x value. You can take x equal to 100, x equal to 10,000, trying to take a number that's easy for the square. You can also take x equal to 1,000,000, and then root of x will be 1,000. That way you can kind of roughly see where the value is. So one of the methods is try it with number let x equal to increasingly large number because x is approaching infinity. Another method is try to analytically analyze the relation between the numerator and denominator. So you can imagine if x is approaching infinity, of course, root of x will be approaching infinity. So basically the numerator has a quantity that approach, there's a negative sign in front of the root of x. This negative sign will not be affected by inside here. So the value is going to be negative because the negative sign on the outside. And remember the sign before a term determine the sign of that number. So we have negative root of x. So this term is a negative value. So you have 3 and a big negative value, and denominator you have 2 times a big positive value plus 5. So that's really the main value in the numerator and denominator. So we try to calculate and think about how we handle this kind of calculation. I mean, like I said yesterday, if you try to determine the value of limit, there's 3 methods: numerically, graphically, which would be the left side. Oh, in this case, it's the right limit, so it's on the right side of your entire graph. Let me see if you already have the answer. I opened up the scanner. If you are online, you should be able to answer the question with your link. I have the sound open on my side. Are you able to hear now? Lauren, do you need your link? Okay. Lauren, I think you haven't attended virtually before, so let me post your link. I checked the sound system on my side, so I make sure that both of the mic is on the computer and on the app. So there are 4 students attending virtually. I can see there are 4 of you. Okay, so if you are ready, you can submit your answer. Right, thank you. Okay, thank you. That's right, thank you. So at limit at infinity, if you want to calculate analytically, you have to work on simplifying the limit calculation. In order to simplify limit at infinity, we focus on the highest degree in the numerator and denominator. You can see the numerator, there are 2 terms. This term is degree 0. This one has degree 1/2. Okay, so essentially root of x is the same thing as x to the 1/2 power. So we have 1 term with degree 0, 1 term with degree 1/2. So obviously the degree 1/2 is bigger. And when you want to keep it, see the negative sign is an essential part of the root of x term. So there's a negative sign attached to it. It's part of it. First term is 3. Second term is negative root of x. So we have a negative term in the numerator that is significantly larger than the other term. So the numerator, you can simplify it since we're talking about infinity. We focus on the highest degree, so it's going to be negative root of x. That is going going to affect the limit at infinity. In the denominator, we also have a degree 1/2 term and a degree 0 term. The number is degree 0, the root of x is degree 1/2. So we keep the 2 times root of x. So it's going to look like this. Right, root of x. We can simplify the root of x because it's a common factor between the numerator and denominator. You see it at the top, you see it at the bottom. So then for a fraction, if there's any common factor, we can cancel it. So now we have this, and then x approaching infinity. At the last stage, we can now remove the limit notation because it's a number. A number is constant. It's not going to be changed by the x value, big or small. So that will be the entire calculation. We do it analytically. So you should be able to submit all your answers if you are.
So how did you get the square root?
How
did you take that out?
We cancel it because it's in the numerator and in the denominator. You see, this is what we see. We have a negative root of x in the numerator, and we have a 2 times the root of x in the denominator. The 2 and the root of x in the denominator is multiplying. When you have term that's multiplying, they are both factors. So we don't have separate terms, so that's a factor. Then the numerator have -1 and the root of x. So the root of x is a factor. So root of x here, root of x there, that's common factor. They get canceled. That's why we simplify it. So only when they have in common that we can cancel it. So here we cannot cancel. This is subtraction, that's a addition. So the numerator, because it's subtraction, these two are not factors. And also because it's a 2 root of x plus 5, it's a summation, it's not a factor. Only with multiplication for the whole thing, then we have factors. So after you remove the number term, we have a single term in the numerator and a single term in the denominator. We then can cancel the common factor. So I occasionally see students, they will cancel it right there at the beginning, and then they will end up having 3/5. And that can be the case because you can only cancel it if you have factor. You can only have factor if you only have multiplication. So this is the only multiplication in the numerator and denominator, and that has summation and subtraction. That's why at the beginning we were not able to cancel the terms, but after the second step, now we can cancel.
So how did you get it?
Oh, this is what we would do. Let's try to explain the power. A root function is the inverse of the square function. For example, if you have x squared equal to, let's say 4. Okay, so if you want to solve it, you will have to take the square root of both sides of the equation. So that's gonna like root of x squared will equal to root of 4. So this root will cancel the square. So then you have x equal to 2. I think there's actually 2 roots. Plus or minus 2 would be the solution for the equation. So in this case, we remove the power in the process. So what will happen here, you will have to take the square root of the left side and square root of the right side. So you remove the power from 2 to 1. And you also remove the number 4 to 2. So we can do the same thing because exponential number, the exponent, affected the power. So we can read both sides of the equation to the 1/2 power. So say you have the beginning, I'm just trying to compare with the two calculation, x squared equal to 4, and then you can raise the left side to the power 1/2. And then you can raise the right side to the power 1/2. And you can see this way, the power of the 2 multiply 1/2. 2 and 1/2 are reciprocal. So 2 times 1/2 is 1. So that this 2 cancel that 1/2. So on the left side, you actually have x to the power 1 because 2 times 1/2 is 1. This is equal to 4 to the power 1/2 power. Our calculator can show this is actually 2. So square root of 4 and 4 to the power 1/2 give you the same number. So they're essentially the same kind of calculation. To me, it was just a different notation to write the same thing. So whenever you see a root of x, you immediately can write x to the 1/2 power. There are other examples of root function or root notation that follow that same reasoning. For example, let's say you have cube root of, cube root of 8. Okay, what does it mean? It actually equal to 8 to the power of 1/3. If you pull up your calculator, you're gonna see this is equal to 2. So you can use your calculator to check cube root of 8 equal to 2, 8 to the 1/3 power also equal to 2. Just want to clarify a lot of situation when we see root. For example, what if we get fifth root of 7 squared? Sometimes you see weird notation like this. So you have a root function outside and you also have a square function inside. So sometimes we may have problem like how do I enter that in my calculator? So enter root sometimes can be a little bit tedious. In fact, we can convert it to a fraction as a power. So you write 7. And then let's write a fraction for the power of 7. The square is a true power, which goes in the numerator. The root will always be a fraction as a power. So the root 5 goes in the denominator. So 7 to the power 2/5. 2/5 power. That is the meaning of fifth root of 7 squared. Just want to refer back to whenever you see like a complex root, how do you turn that root into power form and do it? Any question? I mean, try to understand fractional power as root is very useful because later we might want to find the derivative of root functions. They tend to be hard to calculate. And what we're going to do is we rewrite the root form into a power form, and then we can apply power rule for finding the derivative. So it tends to be algebraically speaking or formula with fraction as power. Made it possible for it to connect it to any power function, but we write it as root. It follow the underlying idea that root is the inverse of power function. So square power and root function, they're inverse of each other. But it made it harder for a lot of maneuver for like differentiation, integration. So situation like that, and also even putting into a calculator. I find it easy to put in a calculator on that instead of putting it here, but there are many calculators that do both. You can actually check if they have the same value. They're just different notation for the same concept, same expressions. I hope that clarifies this. All right, so we're going to repeatedly talk about the root when we are trying to talk about derivative of root function, which kind of is a extension from the power function differentiation. Okay. I hope that we have already all answered the same question. The answer should be A. Any homework question you want to ask? Did you get to answer? Not yet? All right, I saw that you came in a bit later. So the solution, it was in here. That was a part of the solution. Katya? This is the way we calculate it.
I was looking through it
Yeah. Okay. Any homework question that you want to ask before we continue with chapter 2? Any question? Right. Those of you attending online, do you have any question that you want to ask before we talk about chapter 2? Any question? Okay. All right. Because I may not be looking at the Teams app all the time through the whole class, if you have any questions, it's easier to turn on your sound. There's another way I think you can tune in. So that would be a way to attend. Oh, there's a way to attend. Yeah, there's a number that you can call in to make a sound, because I feel like none of you are turning your mic, when we're in class. But if you are trying to see something during the class when I was just showing something off the screen, then it's easier if you can voice your concern or speak out your question. Most of your devices do have a mic, but I think you guys don't want to turn on the mic. But sometimes it's easier to turn on the mic and ask questions. Again, if you have any question, try to speak up. If there's no one bring up any questions, we're going to continue where we left off with 2.2. All right, we're starting to talk about derivative, and we have introduced a derivative definition in 2.1, and we started talking about how we understand derivative in 2.2. 2.2 is interpretation of the derivative. And this is not the first time we've started talking about the interpretation. We did start talking about last week. Basically, once we know how to calculate derivative, we want to find a way to make sense of it. Like, how do we use derivative for any kind of purposes? So when we first start talking about it, the number one interpretation is think of it as instantaneous rate of change. So it's not, the word rate of change is not new, and we have mentioned a couple of times, rate of change can be calculated for a single point or between two separate points. If you're calculating rate of change between 2 points, you're calculating average rate of change. If you're calculating rate of change for a single point, you will be calculating instantaneous rate of change. The instantaneous rate of change is a derivative at that point. The average rate of change is a slope connecting those 2 points. So it really depends on the given information that affects how we interpret it. The example in the book talk about the meaning of the derivative in the world population. So that is back in January 6, 2012. The population that day at 12 o'clock this is a really large number. That's the P0, and the P prime is given at 156, but it's representing 156 people per minute. So we're really calculating the difference between the population between 12 p.m. and 12:01 a.m. So that just in 1 minute, how much population has grown, and I would take that as our derivative. So this also brings up another situation. In real life, data are now being presented as a function. You might think of it as a function like P0, but what about P(x)? Do we actually have a formula for the world population? We don't. So in real life, we have to look at it in a separate, like point-to-point point of view. You can calculate population at every minute, and you can record the change in the population. And those are being considered as one as function value, one as a derivative value. That's how do we take data and actually make sense of it? The second example in the book is talking about a relation between number product and profit. Theoretically speaking, the more product you're making, the more money you're making. Right. So here we have information says making 1,000 product, the profit is 500. So on that, based on that point, that point's tendency, it looks like the derivative is 0.25, which indicated if you make one more product, like 1,001 product, you're earning 0.25 cent, $0.25 more. So it's the derivative is positive when the derivative is positive, and it's indicated a positive change. Once again, derivative represent rate of change. So when you have a positive derivative, that means the change is going for the positive direction. That means increasing value. So 0.25 is increasing 0.25 for every more product you're making on top of the 1,000 product. So what here is talking about, what if we're making 1,100 product? What's the profit? So of course, if you're making 1,100 at the bottom right last calculation, you can see 1,100 definitely should be more than making only 100 product. So it should be the profit at 1,000 plus plus some change. So here we're going to take the derivative as rate of change. So that's going to be multiplied to the actual change in number product. So that will be the 0.25 times 100, which gave us $25 more. So which the calculation will be 500 plus $25, that's $525 profit. So making 1,000 more than 1,000, that profit increased. Any question? All right. So this whole process in comparison with P1000 with P1100 is giving us the idea that sometimes we can use derivative as a way to predict what will happen if you make more, what will happen if you make less, that kind of tendency. So here is one of the purpose or one of the usage of derivative is to do approximation. Basically, the approximation process is you know the value at FC. So you know the function f's value at c. Now you're trying to find out what is the function value at c plus h. Now compare c plus h with c. You have h more. So the differences in the independent variable is c plus h minus c. The difference is h. So that h is a change. The h is a change in the independent variable, but what do we call the derivative? Derivative is called rate of change. So using that rate of change, you multiply by the independent variables change, which then give you the dependent variable change. So the part that says f prime times h is calculation of the change. The part that says f of c, that's the original number. So from the original number to the new number, this is a part of the change. So if you add this part of change to the original number, you find the new function value. And which we did over here, back in this example, we are trying to find out what about z20 if we already have z25. So in this example, I think this is the example that we ended. If you have z25 and you want to try to find the 20, then obviously between the 20 and 25, how much is changing? We're going down, right? 25 is given, trying to find 20. So the independent variable change from 25 to 20, the change is -4. So the h is -4. All right, so I think we did this example last time, but as we were trying to work out more example on how do we use derivative for approximation, kind of have to figure out a way to handle this kind of question. And then the thing is understand the notation's meaning. Right, so you can think of this one, the f of c, as the old y value, all right? And then those, you can think of this as the new y value. Okay, so basically the new y value equal to the old y value plus the change. And then right here, that h, you see the h is what we have in the derivative definition, like f. Remember what will happen? We have f of c plus h minus f of c over h. And then we got that something that's not here when h approaching 0, this is equal to f prime c. That was the definition for f prime c. So f prime c, how do we calculate it? We got f of c plus h minus f of c, and then we divide it by h. Right, so that gives us this idea that what if we multiply the h? The division, right now it's in division format. You can multiply both sides of the equation by the h. That is, you forget of the limit notation. Remove the limit notation, multiply both sides by h, and you have f of c plus h minus c. Minus f of c is f of c times h. Therefore, if you add f of c, you have f of c plus h. So essentially, this is kind of relatable to the derivative definition. So this h there is that h there. The h is representing the change in the x value. If I try to write instead of write change, I just write delta x, change in the x value. So x value change from c to c plus h. So the change is c plus h minus c. That's how much it changes. Now the f prime c is at that point at c, what would be the ratio between the changes? So if you multiply the change with the independent variable, you figure out the change in the dependent variable. So rate of change will be applied to the true change, which then give you the overall change to the y value. So following that idea, we will write the same thing over here. If we want to calculate Z20, we're going to calculate it using the Z25. So the idea is that 20 and 25 are close, so that you know that the 20 should be relatable or similar to the 20 by a little change. So how much is that change? You have to calculate the change with your derivative. So this is approximation, so it's not exact value. Approximately the 20 multiplied by the prime 25, the derivative at 25. So I'm copying what we have there. So f of c is z20, f of prime c is z prime 25. This you were supposed to multiply the change, right? Or you are supposed to multiply the h. So exactly what is the change? What is h? H is the same as delta x. This is the same notation, which then equal to, how do you calculate change? You take the new value minus the old value. So this is supposed to be the new x value minus the old x value. I mean, how do we know which one is old, which one is new? The one you're calculating is new. The one that's 20 is a new one. The one that you already knew, like D25, you put 187. Now we already know. So 25 is considered the old x value, and 20 is when we're calculating. That's the new x value. So the calculation for this part will be 20 is the new one, and 25 is the old one. 20 minus 25, which gave us -5. So that's the h. That's the h. Should try to separate them. Okay, so knowing the change, we can now go back to the calculation. So the 25 is 187, and the derivative is 17, but the change is -5. Okay, so we will follow the order of operation. This is multiplication. We do multiplication before we do the summation. So it's going to be 187 plus. This is a -85. So 187 plus -85 is the same as 187 minus 85. So that's 102. So our answer to the question will be the value of the 20 is roughly, it's an approximation. These are equal, but this is not equal to this. There's limit notation in the middle. So this is approximation because we skip the notation of the limit notation. If you set it equal, then time h add f of c, you get this. So that's why the approximation going on, because we are omitting the limit function. Any question? So that's the process of I'm trying to use derivative for approximation. I wonder if I assign the homework this section. I feel like I probably assigned it 2.1. Oh, I haven't really assigned.
The last one you have posted is 2.1.
2.1, right? So I have really posted a 2.2. We can try a question on that section. I haven't really assigned it yet. Okay, so this is 2.2. Many of them have graphic picture with it because we're understanding the derivative and from the interpretation side of it. Right, let me finish talking about this, and then we're probably going to try these a couple homework together. All right, so this is the first interpretation, understanding it as instantaneous rate of change, and then another thing about the rate of change is what is relation to motion. This is something we often talk about it in physics. Suppose you have a function that represents the position of a moving object, then the derivative of the position function will be called the velocity function, and then the derivative of the velocity function, which is called the acceleration function, So S prime T is the Vt. So S prime T is velocity and velocity is the Vt. And Vt's derivative is acceleration. So Vt is the derivative of St. And therefore acceleration, sometimes we call that At. At is the derivative velocity and it's the second derivative of the position function. So there is a sequence of derivative that we should be calculating when we talk about motion. But this is the relation between the derivative that we're calculating and the motion in physics. We will be coming back to these objects, but then let me try to just conceptually talk about it. And when we are looking at numerical example, we might have a better view of how this is affecting the calculation. So basically, S of T represent the position. Okay, and then S prime of T represent the velocity, and then S second prime, which is the second derivative of T. So you can find the derivative function, and you can find derivative of the derivative, which will be second derivative. Actually, the process can go on, but most of the time we use parabola to represent the position function. So essentially, that's degree 2. Degree 2 functions derivative degree 1. Degree 1's derivative, so that second derivative will be degree 2, degree 1, and degree 0. So if you try to find derivative degree 0, it will still be degree 0. So there's really no point of going on. But there are functions that you have to keep calculating derivative, and there are no ending. So there are functions that has nth derivative. So this limit definition of the derivative, it looks complicated, but the process actually can go on and on, right? So we were calling this one is being called the position function. This is a position function. The derivative of the position function is called the velocity function, and the derivative of the velocity function is being called the acceleration function. Just try to name a couple things that we will see again later in calculus or in physics. So the derivative of the velocity function, we actually gave it a new name. We can kind of name it as Vt. So these two are essentially the same thing. It's easier to write things without the prime notation. And the second derivative is sometimes we call it acceleration function. Sometimes we just simply write it as At. Or you can also, you should also know that's the derivative of the velocity function. So as the process goes on, this is a fundamental function. Position function is one that is most difficult to describe, and we have to know a couple of common features to know which function actually model the position function. So the other two are derived, their first derivative and then second derivative, they're derived from your position function. So describing the position function is a key thing when in terms of modeling, in terms of physical action, modeling the physical action. So once you have this function, the finding derivative, it won't be as difficult. All we have to do is apply them. Just right now, we're just explaining the notation. Any questions? Have you guys had physics? You did? Right, so you know that acceleration is connected to force, right? So acceleration multiplied by the mass equal to the force, and then so then everything will come together. The visual movement is now connected to the physical quantity of mass, right? This just understanding the derivative from conceptual point. All right, this is a part one. The first step, the interpretation of derivative is instantaneous rate of change. So things like a velocity are also a form of the rate of change for anything that moves for motion. All right, second derivative is a geometric understanding. We see the derivative value is actually equal to the slope of the tangent line, which then give us the formula for the equation of the tangent line. So here we have the equation of tangent line. This should look familiar. The left side doesn't matter. Sometimes we write y, sometimes we write L of x, sometimes we write f of x. It doesn't matter how you write the right side. It really is supposed to be the dependent variable notation. What's important is the right side. Yeah, left side is it could be changing. You can write y, or you can write y of x, or you can write L of x since it's a line, so you use L sometimes. But the right side is the formula for the tangent line. So we're just saying the derivative, which is f prime c, the derivative is the slope of the tangent line, assuming that you have that point C identified. So the slope of the tangent line is not the derivative function, is a derivative value, a number. So you have to plug in a number and calculate that value that you, because slope of the line, this is still an equation over the line. Equation of line is supposed to be degree 1. So you can only have one x. The x minus c, that x is the only x in your entire equation of the tangent line. So occasionally I have students, they write the derivative function right there for f prime of c. It's f prime c, not f prime of x. So there's no x supposed to be in the derivative part of the tangent line equation. So try to remember that the slope of the tangent line is a number that should be calculated based on your derivative function. So we're not putting a function there, we're putting a number that calculated based on the derivative formula. All right, this is not new. We had a couple examples in section 1 about calculating derivative tangent line, but it's worth mentioning that geometrically speaking, the value of the derivative is the slope of the line. So by looking at the line, the tendency of line, we identify whether it's increasing or decreasing. If we review what we know about a line, is the line, it goes from the lower right to lower left to upper right, it's the increasing line. If it's horizontal, the line is constant. If it's going from the upper left to bottom right, then it's a decreasing line. Are we okay as far as the slope? So the slope is actually the derivative related to the derivative calculation, and we can actually identify the slope by looking at the line. All right, so let's try a couple practice questions that we might be seeing on 2.2. I was probably going to change this a little. Start with something more relatable. Right. So let's try a question that's easier at first. So this is a question where the function is graphed. Down here, we're trying to find the derivative of some of the special point. What you can see, you can click on the picture, and then from the picture, we can see what was the slope supposed to be. So for example, the first one is try to find the slope at 1. So maybe I should try to copy off the picture, and then we can then talk about slope at different points. That was the picture, and we were supposed to calculate, determine the value of those points. All right, so start with the first one. We want to try to find the slope at it's easier. All right, the first one is f prime 1. So we want to find out, you go find a 1. All right, just try to pointing to that point. This is a 1 on the graph. And then you can see what's the slope. You see from the picture, what's the slope at the point 1? It's 0, right? It's horizontal, yes. Right. So when it goes this way, horizontal, it's 0 for slope. If it's this way, it's positive. If it's this way, it's negative, right? It goes up and down or horizontal. If it's horizontal, well, maybe I should try this. And this is when you have positive slope. This is when you have negative slope. And this is when you have a 0 slope. So from left to right, from here, I do see a horizontal line. So therefore, the slope must be 0. Are we okay?
Yeah.
So this is understanding the derivative as slope of the tangent line. So we're going to answer 0 right there. The second question is asking what is slope at 2? 2. So you're going to find 2. And you're going to find the graph, which is there. Okay, so what's the slope?
0.
So 0, yes. So it's 0. And the next point, we're going to find the slope at 4. So 1, 2, 3, 4. So that's 4 right here, right? So what's the slope then? 1, right? Yeah, so it goes this way, but looks like it's this much and that much is 1 to 1. So we can see that the rise is 1 and the run is also 1. So it looks like the whole thing is straight. So every point over here has the same slope, which is 1. And the next one was talking about 7 to go 5, 4, 6, 7 right here. Right, so at 7, what's the slope?
0.
Also 0, right? So it looks like we are reaching the bottom of things. Over here is decreasing, over here is increasing. So what happened in the middle is not increasing, it's not decreasing, it's horizontal. So there we have a 0 slope. So whenever it goes down like that, it's negative slope. And whenever it goes up like that, it's positive slope. Whenever it's not going down, not going up, like hovering right in between the faces. It just turned from decreasing to increasing, but right in the middle of it, it's 0. Okay, so we see a couple of key points here, and we have to notice that at 3, which over here, there's no derivative. This, it should be D and E, and here is also D and E. Whenever you see a sharp point in the process, that's the point that we have to pause, right? That one has no derivative. Like I said, if the entire function has derivative everywhere, it will be a whole smooth curve. But whenever you run into a sharp corner there, and that's normally in real life, if you're designing the highway, it should be smooth out, right? It cannot be that way. Whenever you have anything sharp, something is wrong, and we have an undefined derivative there. So that was that example just to illustrate relation between the graph and the function itself. So then at also 0, at 4 is 1, and there is 0. That was this example. So most of these questions have that. And this is the problem 5. That was like an old version of the homework assignment. I'm probably gonna assign them today, but we haven't really assigned a 2.1. This question is asking if you have the function is -6, the derivative is 8, what is the equation of the tangent line at x equal to 5? So these are one of the questions that we don't have the function formula, but we have a couple of information that we got a derivative, we got the function. Now what about the equation of the tangent line? So these are one of the question exercise in the second interpretation. The derivative is the slope of the tangent line. So to calculate equation of the tangent line, you gotta remember the formula. It was a y equal to f prime of c times x minus c plus f of c. So that was the formula. We gotta know how to use the formula. Now this c is keep popping up. You have a c in here, C in here, and C in here. C is a point of tangent, say, like where are you drawing this line? See here, we're at x equal to 5. We're drawing the tangent line at this point. So that's our C. So in our case, the C is equal to 5. Once the C equal to 5, you know that is going to be x minus 5 because C equal to 5. Once we identify the C, we know how to fill in all those numbers in. But then here it should be f of 5 because C is 5. And here is going to be f prime of 5. So as we were trying to fill information out, we realized a rough, like roughly the structure of the whole equation, but it's not the answer because the f5 and f prime 5 are number that should be our abstract notation that should be replaced by the actual number. The C is 5, f prime of 5 is -6. So this f of 5 is -6. So that one is you cannot keep it. You have to replace it by -6. This is okay. Trying to piece together this entire equation. Over here says f prime of 5 equal to 8. So that means this has to go. That is abstract notation. In the actual equation for the tangent line, you have to replace this by the actual number. That's f prime is 5 is 8, so 8 is replacing the entire notation. Don't leave any F or F prime in your final answer to see how we answer. So you can answer your tangent line equation just by that form, but if you want to simplify it, that's fine. Entering this way, or you can enter y equal to 8x. 8 times 5 is negative 40. 8 times negative 5, negative 40, and then there's minus 6. Now we're going to combine terms. There's only one x term, but there's two number terms. The negative 40 and negative 6 can be combined into negative 46. So this is to format of the equation. This one is being called the point slope formula. A term, because we have the 0.56 and we have the slope, which is 8, and that's being called point slope formula. And you might refer back to your algebra book, point slope formula. Okay, and then over here, the bottom one is point slope formula. Slope intercept formula? Yeah, we have our slope in the equation. We also have the intercept, which is a negative 46. Intercept. Well, okay, so these are the two names that was very visible in our algebra book when we talk about equation line. So they are representing the same line with different format. As far as this question, it's easier just to enter the 8x minus 46 because it's way shorter than the formula. Or if you want to write the original way, you can also just write x minus 5, and then there's minus 6. Okay, so that is the point slope formula, and that's also the same thing, right? And then it says this is equivalent to the one you just submitted. So basically, the both answer are equal to each other. They're just the same thing. Any question? Right, the tangent line equation really follow the way we understand equation with tangent line. The whole thing is, as long as we can apply the formula correctly, normally we don't have a lot of issue with the equation tangent line, unless if you put in the wrong number. Occasionally, you have students, they have accidentally put the 8 over here and 6 over there. So if you have them mix up, and we might have small errors for the equation tangent line. But the rate of change or approximation are the one that actually might have some issue. These couple other exercises. Let's see. Okay, so this is another question where we have equation. The tangent line is going at the tangent line is x negative 6, 4. It passes through the point 2, 1. The question is compute the following. Let's calculate the point. Let's calculate the derivative. Okay, and this is the kind of thing that we might have. We might have to have a little bit better understanding of the equation tangent line in order to understand it with no issue. So what we can do is really identify those things. Okay, so essentially we're saying that you got a tangent line, and on the tangent line, we already have 2 points. One point is a point of tangency that's at negative 6 and 4. So right there, that's the negative 6, 4. Negative 6, 4 point. The other point is at 2, 2, 1. Okay, and then we're drawing a tangent line through them. We're drawing a line, which is being called the tangent line. So this tangent line is going through this 2 point. And that's the 2 point that we were given. And it also has here, the tangent line is at this point. So basically our graph is tangent at this point. So this point is your point of tangent. So essentially your curve is like this, okay? Because the graph is a tangent line at this point. So that's a tangent point. On the other hand, this one is a random point on the line. So that's not a point of tangency, right? Pass through the point 2, 1. So point 2, 1 is just another line on the point. But the negative 6, 4 is at that point, that's our tangent line. So that's the point of tangency right there. So now let's try to answer the rest of the question. Number one, let's try to answer B first. B says we want to find f prime of -6, which then should be the slope. So that one is a derivative because the derivative is supposed to be slope of the tangent line. Right, so based on our understanding, slope of the tangent line, slope of the tangent line equal to the derivative. In this case, we do not have the function, so how do we calculate the tangent line? The thing is, we have the line already drawn, we have 2 points. So if you have 2 points on the line, you can calculate slope. Even though originally we know the slope of the tangent line should be calculated based on the derivative, but slope of the line or any line, tangent or not, slope of any line can be calculated as long as you know any point on the line, right? Right? So we may not know how to calculate slope of the tangent line. We know how to calculate slope of the line, which the two is supposed to be the same. So what we can do is follow the definition for how do we calculate slope, which then is supposed to equal to y2 minus y1 and divided by x2 minus x1. So the second question, the derivative, all you have to do is remember that we were supposed to be calculating the slope, and slope can be calculated for any line that has 2 points given. So we're gonna subtract the y value. I'll just go ahead calculate for -1. That was the y value subtracted. And you can see the 2 points on the graph, and then the x value is given by -6 and 2. So I'll just take the corresponding y value for 4 is -6. 4, -6. I have 4 minus 1, so now here I have to put in the 6 instead of the 2. The 2. Because 2 is supposed to match the 1. So you make sure you are not using the wrong number each time. So we would do -6 first, and I'm going to -2 because you were supposed to take x2 minus x1. If you take the y2 as the 4, then your x2 has to be the -6. I hope I'm making sense there. So as we're calculating the slope, we want to make sure that we're not making mistakes, putting the x1, y1 and x2, y2. So numerator end up being the numerator end up being 3, and the denominator is -8. So the whole fraction, I guess we should put the negative in front. So it's -3/8, and that we got to. The answer to the second part is -3/8. Right, in the first question, okay, f of -6 is the y value that matches the -6. Here, if x equal to -6, the y value should be 4. So the first one simply should be the point of tangency, the y value for the point of tangency. At the point of tangency, -6 is the x value and the 4 is the y value. So part A, we do not have to calculate it. All we have to do is identify the difference between the 2 points. -6 and 4 is a point of tangency. 0.21 is a random point on the line, which says it passes through. This is at that point, we have a tangent point, tangent line, so therefore it should be the value. A. Any question? Are we okay? Right, so this is a problem 8. Any other questions? And that's determining the slope of the line. I believe it was like a -1 and +1. This is a absolute value. So what you can do is graph the function, and you can see, I think the easiest way to do this example is to determine the graph, or you can use numerical value, but since now we're understanding the numerical meaning, so x minus 10. Okay, so you can see absolute value x minus 10 is different than the absolute value of x that we are talking about before. If you have y equal to absolute value of x, it's a tangent line at 0. So positive x, you have slope equal to 1, negative x, you have slope equal to -1, which we mentioned before, right? And then now we have x minus 10, meaning that we're moving the x value of x function 10 units to the right. That's transformation. X minus 10 is moving the absolute value of x function 10 units to the right. Minus 10 is 10 units to the right. Therefore, when x is bigger than 10, we have slope that's positive 1. When x is lower than 10, we have slope that's negative 1. So going back to that question here. Okay, so that's the slope. That's y minus y, x minus x. So that's slope below 10. The slope is -1. And this is slope above 10. The slope is positive 1. So that's one way to interpret this. Both of the derivative calculation, both of the limit calculation are derivative value. So this is a left side derivative. That's the right side derivative. And therefore, the function do not have a derivative at 10, because on the left it's -1, on the right it's +1. So joining them together, there's no two-sided limit, does not exist, which is why it's not differentiable. Function is not differentiable. Any question? So that's looking at the slope. That's how we know there's no derivative. On one side it's -1, on the other side it's +1. So that there's a sharp corner at 10. So there's no derivative at 10. Visually, we can see that when we graph it. Question is, right, one of the questions are similar to what we just did. You might have a graph that's given. I'm not sure if you get the same question as mine. The question is to find f prime of 1. Estimate f prime of 1 when you see the picture. So how do we do that? You will have to study the picture. F prime of 1 is right here. So what you want to know is that the blue curve is the curve and the red line is a tangent line. So if you are trying to find the f prime of 1, you are trying to study at 1, we draw the tangent line. So if you're able to calculate the slope of the red line, you then have the derivative. So the process will be like this. We'll identify the picture. I want to draw your own picture. All right, so that's how it's going to look like. And we want to know f prime 1. So you identify the point, which is 1. Right, the red line is the tangent line. So f prime 1 is the slope of the red line, f prime of 1. Essentially would just be the slope of the line. So how do we know the slope of the line? Then you can find 2 points on the line. 1 point is over there. 1 point is over there. So this point, you can see that was 2. There was 1, 2. So this point would go 1, 2. Now what about the other point? That was 2. So 2, 3, 4, 5, 6. So that the other point is 2, 6. And then what you can do is find the slope using the 2 point. Okay, let's calculate it. What's the slope? It's really positive, right? It's just positive slope because it's going up. It's 4, right? Right? 4. So 6 minus 2 and 2 minus 1. 6 minus 2 is 4. 2 minus 1 is 1. So 4 divided by 1 is 4. So we answer the question, hey, the slope is 4 or the derivative is 4. So as long as we understand that the derivative is actually the slope of the tangent line, and we probably will have a plan how do we calculate it. Other question in this site, it's a little bit hard to talk about it because they have pretty complex graph. Like this one has a couple questions. What will be the slope from 0 to 1? I find the point at draw, find the slope between the 2 point 1 to 2.5. 1 is over here and 2.5 is there. And you're going to try to find the point and then connect them and find the slope. So the average velocity will be the slope between the 2 and then the next one is 2.5 to 3.5. 2.5 is here. 3.5 is 3.5 is there. So you're gonna connect them and try to calculate their slope. And then that will be part A. Part A is all average rate of change. Part A is all average velocity, so they are all average rate of change. The second part is calculating the instantaneous velocity, which is the exact derivative. For example, we want to find out what is the derivative at t equal to 1/2. So you might have to go find the 1/2 and try to roughly sketch a tangent line to find out what is the tangent line. So that was one of the assignment that we practiced before. How do we determine the connection between instantaneous slope and the average rate of slope, the average rate of change? Any question? Okay. What about homework? Any homework question? Right, we have 15 minutes left, so allow me to start a little on 2.3. I hope you are okay with 2.1 and 2.2, but you feel free to voice any of your concern as you work through these. My plan was trying to start a little on 2.3. The whole chapter 2 focus on differentiation. Chapter 2 focus on calculating the derivative. As you can see in 2.1, we determine the derivative, we define the derivative using limit computation, but using derivative to calculate, using the limit to calculate the derivative can be a little bit time consuming, and we're always hoping for a faster way to determine the derivative. So here we are, we might be able to follow some of the pattern to find the derivative faster. 2.3 is called basic differentiation rules. These are the rules that will be keep coming back and practicing over and over until it becomes really quick and easy as we practice more and more. So title for 2.3 is basic differentiation rules. So, or derivative of some common functions. We have already know one of the rules. If you have a line, the derivative is a slope of the line is a derivative value. And then what about other stuff, right? So one of these we already mentioned that if you have equation of a line, then the y equal to mx plus b, what is y? Y equal to m. So that slope is the derivative. So that's the one we already tried. Now here we're going to try looking at a degree 2 polynomial. This layout on the board, you see it's pretty complex. The reason it's complex because we actually use notation instead of actual number. So I could be making it easy, just go 2x squared plus 3x plus 9. But instead we're using a, b, c. So ax squared plus bx plus c is the general formula for any quadratic function. So here we're deriving a plan or a formula for how do we find derivative of quadratic function. All right, so the point is we're going to follow the entire section 2.3, follow the limit definition. But then after this section, we now have formula. So we're deriving the formula using the original definition. Once we have the formula, we can throw away the limit definition, actually follow the formula. So having those formula kind of having original available results that we can apply. So we can use this result instead of finding the fundamental results. Right, so here we are trying to find the root of this function. So that's from f of x, we're trying to find f prime of x. According to the definition, f prime of x is supposed to be f of x plus h, which is this. We're plugging x plus h to the f of x. So that's f of x plus h in the first part minus f of x. F of x, you copy the definition for f of x, copy that down. And then realize we talk about when we try to find the derivative using the limit definition. One thing is for sure, the numerator, many of the terms that do not have h will be canceled. So we're hoping to find a way to cancel c. You can see c minus c. C is canceled. And over here you have bx, and there you have minus bx. So the bx is canceled. And over here you have ax squared, and there's minus ax squared. So for sure, the term that in ax squared plus bx plus c, they're all canceled by various terms in the first half of the equation, right? Once those terms are canceled, what you have left is a term that has h. So ax squared is canceled, but the ah squared is still there. And then there's x times h and times 2, and that also times a. So that's that term. So in the term of the expansion of the square, there's 3 terms, but the ax squared will be canceled with that one. So there's 2 terms that is falling over. Right, in the second group, there's bx, there's bh. Bx is canceled with minus bx. So what you left with is bh. That's all that there's left. All the other term in the first line of calculation is canceled because of subtraction. All we have left is 3 terms. Any question? Are we okay? Any question? All right, we then have a division. We divide by h. Anyone that has an h, you get cancel with this h. So that h squared, ah squared divided by h, you have ah. 2ahx cancel the h, we have 2ax. And then the bh cancel the h, we have the b. So after division, there's no more h in these 2 terms, but that one has h. When h approaches 0, h goes away. So what we have left is 2ax plus b. That's the derivative of this function. Any question? Okay. All right. So we're treating this as a formula. The more limit definition we work on, the more things that we can apply as a formula. The more formula we know, that's kind of like the more we save our time in the computation process. So based on these calculations, we realize the result is saying that if your original function looked like this, right? Oh, I'm gonna try to copy. If this is the original function, and what will be this is the original function, and then our derivative function is equal to, then f prime of x would equal to our final answer over here. So we can consider this as a set of formula that is saying, yes, I should put a term if. Because you can define f of x however you want to define it. Suppose f of x is being defined like this, then the derivative is ax squared plus a. So in a way, we're saying if the function itself have a degree 2, then the derivative is degree 1. If the function have an x squared, in the derivative actually we have a 2x. So we still have the a, we still have the b. Another thing is if the original function has degree 1, and the derivative is degree 0. It's a number, right? The bx derivative is b. That's like speaking about linear function. If it's a line, the slope of the line is a derivative. So bx plus c, the b is a slope. So now you have a b in here. So we can observe some common property as we are working through these. And let's try to look at a couple of scenarios. Let's see if you got a function like g of x. Try to make up an example. Suppose g of x equal to x squared plus 5x. All right, using the formula that we just had before in there. And what about g prime of x? What's the derivative? What's the derivative? And based on formula, which is like with x squared, what's the derivative? 2x. 2x, right? With x squared, we have 2x. And then what about the a? In this case, we really do not have an a. See, there's an a, but we don't have the a. Let's take a equal to 1 there. So that would be a 1. Therefore, let's say 2 times 1 times x would get 2x. So applying the above formula, we're coming up with a calculation of any other function. So we're treating this as a formula, but as you can think through it, you have to learn how to like adjust the formula to the point that you can do it with for whatever function you're saying. All right, that's the finish. What about the 5x? What's the derivative? It's just 5, right? So the answer will be 2x plus 5. That's the derivative for this function. This is a pair of relation between the original function and the derivative function. Give us a couple of scenarios to work around. Right, let's try to make up another example. For example, if we get h of x equal to like negative 2x square and then minus 9x. So what about the derivative of this function? Equal to, what about the negative sign? So it's negative 4x, right? I think I should erase that thing. Maybe that would be. So the answer to the derivative should be negative 4x. For 1, it should be lower the degree, original function degree 2, the derivative will be degree 1. If the power goes down. Another one is coefficient. Instead of a, now we have 2a because 2 goes to the front. So that 2 will go to the front. The 2 on 2 multiply give you a negative 4. So negative 2 times 2 is negative 4. And then we follow that by negative 9. Okay, so this is how we differentiate a degree 2 polynomial, finding its derivative. So I hope this provide a couple examples by applying that formula. Any question? So we're trying to knock off one example at a time. So the more example we see, the bigger variety of situation that we can handle. Right? This is that example. And now is another example over here. If you have 6x squared plus 11x minus 13, derivative 6x squared is 12x, derivative 11x is 11, derivative negative 13 is 0. If you only have a number has 0 derivative, that's like having a horizontal line. What's the slope of a horizontal line? 0. Yeah. So it basically, it still follow the idea that derivative is supposed to be the slope of whatever curve that you're seeing. All right, so here we got a bunch of other stuff. Instead of doing it one by one, so the limit definition, we didn't exactly follow every limit definition. In fact, we're bringing out their formula. Number 1 is a most simple case. If you have a number, derivative of a number equal to 0. This is a ddx notation. This looks a little bit different than before, but we're trying to get used to it. The ddx notation allows us to pair the original function and the derivative function in the same spot. All right, so the equation 1, formula 1, is saying derivative of number equal to 0. The second formula says derivative of the power function, you have to bring the power to the front, and then the power minus 1. Just like x squared, if you have x power 2, if n equal to 2, 2 go to the front, and then 2 minus 1 is 1, so that's 2x. So ddx of x squared is 2x. ddx x cubed is going to be 3x squared. So that's this rule number 2 is also called power rule for differentiation. So it allows us to differentiate or allows us to find the derivative for any power function, whatever power that is. The power can be, here is the power is an integer, but later we're going to show that the power can be a fraction. The power can be a decimal, so whatever power it is, the power can be a negative number. You can still apply power rule for differentiation, except when the n equal to 0. So the power equal to if the power equal to negative 1, that's still apply. Will it be that situation? All right, I think any power you can apply power. I was thinking about in integration there. All right, so number 3, rule number 2 is a power rule. Number 3 is relation between sine and cosine. Derivative of sine is cosine. This is something we tried before from section 1. We try using the limit definition. We find out derivative of sine x is actually cosine x. Right, that's rule number 3. Actually, we also talk about derivative cosine. Derivative cosine is negative sine. So it's like sine had derivative cosine, cosine had derivative negative sine. So they go a little bit reverse, except they are having that back and forth relation between each other, which follow the idea that sine and cosine are full functions. So that's number 3. Number 4. Well, number 3 and number 4 are together. Number 4 saying derivative cosine is negative sine. And number 5 is different. Number 5 saying derivative e of x is e of x itself. And exponential function with base e exponential function is the only function where the derivative equal to itself. So there's no change. Before there are similarity between the original and the derivative. You can see derivative number is also a number, except that number is zero. Derivative of a power function is a lower power function. Derivative trig is another trig, but they are all similar between original and derivative, but only number 5, only exponential function. Not only are they similar between the original and derivative function, they're identical. There's no change whatsoever. What you have as the original, now you have it as derivative. They're exactly the same, and that's the only function that happens. So eventually, later, when people are making mathematical proof, they're trying to find derivative. If a function's derivative equal to itself, we say that has to be the exponential function, because exponential function is the only function that has that behavior. Inside original and the derivative equal to the same thing. All right, it looks like time's up. So these are the formula we're trying to recite, and we're gonna apply them to solve other kind of question. Having these formulas probably will make the differentiation faster, so we don't have to look at the derivative all the time. And that'll be for today. Tomorrow and Wednesday, we'll keep practicing questions related to the test. So please make sure that you voice any of the question, any of the hard questions. We can talk about it ahead before. I'm probably gonna talk about the practice question for test 1. So that way, hopefully by Thursday, we'll be able to practice the example on the test 1. You too. All right, that'll be it for today. Thank you. I think whatever way that allows you to figure out the answers fine. It could be in a particularly universal way or graphic way. As long as you have your reasoning and your answers right, fine. Yeah, it's okay.